All right, we'll get started. Happy Monday, happy 10th week, and hope you guys are doing well. I apologize. I don't have a description of the final exam ready just yet, so I guess I'll reveal on Wednesday. Okay, what will be on the final. So still kind of putting it together. The goal isn't to make it crazy hard, but yeah, so just still getting that prepared, but I'll let you know what the final will look like. Okay, well, I thought we'll continue and finish up this document clustering problem, or this thing that I introduced on Wednesday. All right, so again, the premise here is that we have a set of quote-unquote documents. Documents are basically just sets of words. So we're using a bag of words model. So again, the idea is, almost like in a cartoon, you have this piece of like I think sometimes in a cartoon you have like the character, they have like a piece of paper with words on it, and then they shake the paper, and then like the words fall off into the bottom, right? And that's kind of like the bag of words. So imagine somebody writes, what do we call them? They're no longer called tweets, but right, so a tweet could be considered a document, but then again, you like shake it, and then it's just like the words fall into the bottom of a bag, okay? Or it could be an article from the newspaper, or an article on Wikipedia, and then again, you just kind of, the structure falls apart, but you just have these words, okay? And what we're doing is we're looking at the count of the words to give us information about the document. So when it is bag of words, good, not bad, ends up having the same meaning as bad, not good, okay? Because they consist of the same exact set of words. So that's one of the limitations of bag of words. But anyway, this is where we are. The other kind of issue with, or the problem that we're facing with document clustering is that we don't have a predefined dictionary, or we don't have a lexicon that has already been trained to decide what are the probabilities of these different words. So if you already have a lexicon, okay, so I took this lecture from 102B last year. This one, it's not working. In the document classification works in a way that you have these lexicons that have already been pre-trained, okay? Let's say these are the words, and depending on the classification of the document, these words show up with different probabilities. And so, we said you could have fairy tales or you could have chess, and if you see the word evil in this document, it's much more likely to be a fairy tale than it is about chess, because it's unlikely for somebody talking about chess to talk about evil, whereas, a common theme in fairy tales is this idea of good versus evil and things like that. So we would have this if it were just a classification problem, but we don't have a classification problem. We have a clustering problem. And in the clustering problem, all of our documents come in, they are unlabeled, and we need to sort them. But how do we sort them if we don't even know which ones go which way, right? So just kind of based on the counts of words, can we form two clusters? And that's kind of where we are. We have this hierarchical model, and we say the way our words are being generated, or our documents are being generated, okay, and documents are basically word counts, is that first we flip a coin, okay? The coin is weighted and it lands heads with probability pi. And so if it lands heads, then you'll have document class 1, and if it lands tails, you'll have document class 0. Okay? That pi is this probability of landing heads comes from a beta distribution with its own hyperparameters. Okay? And then once you have the label, whether it's a 0 or a 1, that's going to determine kind of this which vector theta to use. So theta is the kind of the equivalent of the vector of word probabilities, except now defined on the entire kind of English lexicon. What's the right word, right? The set of all words in the English language, whatever we want, 10,000, 80,000 words, however many words we want to have in there. We have kind of a theta for class 1 and a theta for class 0, except those thetas are unknown, but this is the idea of how our words are structured. And based on that, we do a multinomial draw from theta with n words. So we say, I want to create a document with 100 words, and we're going to select basically 100 random words using the probabilities in this vector theta. The vector theta itself comes from a prior distribution defined by the Dirichlet. The Dirichlet distribution is the multi-categorical generalization of the beta distribution. So beta distribution always returns a value between 0 and 1, and the Dirichlet distribution also returns values between 0 and 1, but it's going to return a vector of values between 0 and 1, and that vector values will add up to 1. But if you say, like, I want Dirichlet, 555, you might get 3 values, 0.3, 0.4, 0.3, or something like that, where these 3 values add up to 1, but reflecting kind of sort of equalish probabilities. You could get 0.35, 0.35, 0.3, okay? If you say, so in the way that, so if you remember the beta distribution, so if you have beta, say 2, 2, 2, between 0 and 1, you have kind of this wide shape. And as you go, beta 10, 10, between 0 and 1, you get something centered closer to 0.5. And if you do beta, say 100, 100, now you'll get something, very closely less spread around 0.5, right? Same kind of thing, but with Dirichlet, you provided a vector that is, with however many kind of categories of pseudo-counts. So if I do, say, 5, 5, 5, all right, now I'm basically saying, like, I got 3 things, and so the Dirichlet will produce 3 values, okay, all between 0 and 1, and these will all probably be centered around you know, 0.33-ish, okay? But if I do, say, Dirichlet 100, 100, 100, now we're going to get 3 values all between 0 and 1. If 0.33 is right here, then we're going to get much more like three things very kind of tightly bound around 0.33. And likewise, it doesn't have to be, these three values don't all have to be identical. You could have, say, Dirichlet, I don't know, 800, 100, 100, right? And so that's going to put a strong kind of emphasis on the first one being very close to 0.8. And because these numbers are quite high, then this one will be at like 0.1. And then this one will be at 0.1. Something like that. Okay, and they'll all be kind of very kind of tightly wound. All right, and then, you know, if you wanted to have, you know, if I did 300, 300, 200, 200, okay, now I'm going to get four values. And then this one will be tight around 0.3, 0.3, 0.2, and then 0.2. Would again, all of these will have a little bit of spread around each of these things. And so the idea here is we're going to have basically a Dirichlet distribution, but not just a vector of four values, but a vector of 10,000, or I don't know however many words we want to have in our lexicon. Okay, I don't know if this is captured at all in video. Sorry, you guys are missing out on those who are watching on video, which is the vast majority of you. But you know, you'll have like maybe a vector of kind of 10,000 values, and they'll all kind of reflect, you know, however many counts we have on each of these things. And so the random draws will be some value around like 10 to the minus 5, 10 to the minus 4, you know, 2.2 times 10 to the minus 4, or something like that. Let me see if I could just demonstrate a few kind of random Dirichlet so we'll ask for one draw from the Dirichlet using, say, 5, 5, 5, and then let me just round that off to 3. Okay, so this one draw from 555 is 0.258, 0.492, 0.25. Another one is 0.332, 0.242, and 0.425. Okay, whereas if I bump this up to, say, 100, 100, 100, now I expect all of my values to be kind of very close to 0.33, 0.32, 0.378, 0.302, 0.353, 0.31, 0.337, 0.345, right? So hopefully this is illustrating kind of the change in spread by using this. If I did 800, 100, 100, now I'm expecting my first value to be around 0.8 and the others around 0.1. Okay, 0.764, 0.122, 0.114, 0.821, 0.095, 0.085, right? And I think when we add all of these up, they should add up to around 1, maybe off by a little bit because of rounding, okay? And so, you know, here I'm going to have 300, 200, what did I have? 300, 300, 200, 200. I'm going to get four values, kind of close to 0.3, 0.3, 0.2, 0.2. But again, because of random, we get slight variation. But however, whatever we put in here. When you have a beta distribution 1, 1, it's uniform in that any value between 0 and 1 is equally likely. And you have kind of the equivalent for Dirichlet. You can do 1, 1, 1, 1, and this is going to produce four values where the sum is going to add up to 1. But like kind of for the first number, any value between 0 and 1 is like equally likely. And actually, for all of them, any value between 0 and 1 is equally likely. It's just which one ends up being kind of the thing, right? I don't know. But so this is kind of your uninformative prior. You could use that as kind of like your pre-pseudo counts before you look at any of these things. So anyway, but all to say is that we're using a Dirichlet distribution that kind of amasses, after clustering a whole bunch of documents, we kind of amass a count on saying like, okay, we saw the word apple, 222 times, and we saw the word, banana 85 times, and we saw the word cat this many times, and you have this kind of vector of kind of like word counts, and you use that to say, all right, based on the counts of how many times I saw the word apple and how many times I saw the word banana and how many times I saw the word cat, this is now my probability of getting the word apple or banana or count. So that's that. Okay, so this is to say, this is our document structure. We flip a coin, probability of pi, generating heads or tails, and we either get a 0 or 1. Determining the 0 or 1 will determine which vector we have. Theta 0 is going to be basically the counts, or the probabilities that was generated from the Dirichlet distribution. So if I take this Dirichlet set of values, so I have this vector of 4 values. Let me save this somewhere. Okay, so this will be my vector. We'll call this theta. So theta is this vector of 4 values that add up to 1. Okay, sum of theta is 1. And now I can use this to generate a value from the multinomial. So I can do R multinom, and I just want 1. But let's say I want a document with 100 words from the multinomial distribution. Okay, so it says if these are the probabilities, okay, after you generated 100 words, we got this first word 27 times. And then the second word appeared 37 times. This next word appeared 22 times. And then this last word appeared 14 times. Okay. Or we could say, give me another document with 100 words. And we're going to get slightly different counts. 27, 37, 18, and 18. Okay, even though we have different probabilities. Okay, much like if I flipped a coin 100 times, sometimes we would get 50 heads. Sometimes we would get 53 heads. Sometimes we would get 45 heads or something like that, right? But now we're rolling, I guess, a 4-sided die, but it's not evenly weighted. Some sides are a little bit more likely to show up than others. So it's kind of this, it's a little bit odd, but you generate this vector of probabilities first, and then once you have this vector of probabilities, then you generate your word counts. And that's kind of, that's this structure, and that's what we're saying. So we have this vector of probabilities theta, and using that, we generate our word counts, which are given by R sub j here, okay? I'm sorry, no, R sub j is how many words total we have. So this is the vector of word probabilities, how many words total we have in document J, and then W sub j is the vector of word counts. So a document gets boiled down to like how many times did this word appear and how many times did this word appear. And I think we said this already, so our prior distributions are that the probability of getting a 0 or 1 label comes from pi. Pi comes from a beta distribution, and then that vector of probabilities for each word, theta, comes from the Dirichlet distribution. Okay, so we're going to set up the Gibbs sampler in this kind of unsupervised setting where no labels at all are provided as training data, and then and we'll set this up. All right, so the Gibbs sampler is to walk through this k-dimensional space defined by these random variables, and And in this case, the variables that we need to figure out are this probability pi, and then these vectors on word probabilities. And these vectors are really big, maybe 10,000 words if we're going to do a full thing. I'm going to do an example, but with like children's books, like Dr. Seuss books, so that there's only like a small vocabulary, maybe like 60 words or something like that, okay? But it still kind of illustrates the idea here, okay? And then we have a bunch of documents, and among those documents, we also need to figure out whether it was labeled a 0 or a 1, okay? And then we also have other vector variables, wj, which is the word counts, but these are observed and they are already known. So we don't need to sample these here. This is the data that is known to us, and that's what we're using to kind of figure everything else out. Okay, it says initialization of our sampler is going to be easy. Pick a value pi by just randomly sampling from a beta distribution. And then for each j, flip a coin with probability pi and assign that label, either 0 or 1, based on the coin flip. And then initialize theta 0 and theta 1 by just sampling from this Dirichlet distribution, okay, with gamma theta being kind of this vector of pseudo counts. And I think we start off with an uninformative one where we just have a bunch of ones. So the joint distribution of everything is, what is the probability of pi based on your priors? So this is beta, and then the labels based on pi, that's Bernoulli, theta based on gamma, which is going to be Dirichlet, theta 1 based on gamma, also Dirichlet, and then the corpus, the set of all the kind of word counts. So these are multinomial draws based on theta 0, the vector of word probabilities, and then the label, which one we have, corpus of documents. And we said, one kind of nice thing about the multinomial distribution, and it looks like a whole bunch of mess here, but I think we also noticed this when we did the beta and binomial distribution when we were doing baseball, is that you can kind of like multiply these things together. And so one thing that's going to actually simplify our mathematical calculations is that we don't actually need to look at like every single document individually. We can just kind of say like, these are all the documents that we've clustered together into class 1. And what is the total number of counts across all of these documents? How many times did the word apple appear in all of these documents? How many times did the word dog appear in all of these documents? How many times did the word cat appear in all of these documents? And we don't need to look at document 1 had apples 3 times and cat 4 times and dog twice. And document 2 had apple 1 time and cat this. We can just say, documents 1, 2, 3, 7, whatever, these are the ones I got clustered together. And in total, apple appeared 15 times. In total, cat appeared 12 times. And so that's going to kind of simplify our work a little bit. So that's what this is saying. We're just saying we can just kind of take the total word counts, okay, for the NCX here. This is just to say where NCX gives the count of word I in all of the documents with class label X. So either it was labeled class 0 or class 1. We're going to just look at how many times did apple appear, how many times did cat appear, how many times did dog appear. And we'll take those words, we take the probability, raise it to that power. Right, just kind of like binomial, you say the probability of success raised to the number of successes times the probability of failure raised to the number of failures. This is multinomial, so you have probability of apple raised to the number of times apple appears, probability of cat raised to the number of times cat appears, probability of dog raised to the number of dog appears. Keep going for every single word, thousands of them, okay? Or maybe in our children's example, 65 of them, or however many we have. Okay, let me see if there's anything else. I think this is just beta prior. This is a probability for this is just binomial here. This one is, word counts, multinomial. Okay. Okay. So here we want to integrate out pi. So we're going to calculate, what is kind of this thing. So we have our joint distribution of everything, and we're going to say, can we simplify our math by integrating out the pi? We'll figure out what is this quantity across all of the different possible values of pi. Because once we have pi determined, is in that the probability of the coin landing on class 0 or landing on class 1, it could be 0.5, it could be 0.8, it could be 0.2, it could be something in between, or 0, 1, anything like that. Once that is determined, basically everything else in this hierarchical structure is kind of determined off of that. So can we figure this out? Can we kind of figure out this quantity across all of the different potential values of pi? So we have the beta prior distribution, pi based on kind of, your shape parameters, the first shape parameter and the second shape parameter. And then this is the vector of all of our labels here. And so here they just did a little bit of kind of math, and they took advantage. And I think we did this like several weeks ago when we also did the baseball example, where we said we're going to take advantage of this kind of, we understand that you have this normalizing constant with the beta function with, gamma, alpha, gamma, beta, and things like that. And they kind of worked through the math, and they said, okay, well, if you take across all of the kind of how many documents are labeled class 1 and how many documents are labeled class 0, and then you kind of take your prior shape distribution and your prior, this ends up being the normalizing constant. So the analog, when we did baseball, we had kind of these prior counts. I think it was like 81 and 219. 81 and 219 would go into gamma pi 1 and gamma pi 0. And then C1 and C0 would be kind of like the counts of document 0 and counts of document 1. So it'd be like, okay, here's our new baseball player who had 5 hits and 5 outs. And so what you end up getting, your new normalizing constant, is after you did 81, 219, and 5 and 5, it becomes 86, 224. Basically, you now have gamma of 86, gamma of 224 divided by, gamma of 310. That's kind of the equivalent here. It's just we've changed it to like how many documents were prior labeled 0, prior labeled 1, and I think we just started off with uninformative values of 1 and 1. And then after we do our clustering, we're going to get some documents are clustered to 0, some documents are clustered to 1, and we throw those into here. Okay, so that's going to be kind of our normalizing constant. We throw that in there, and so we have the prior normalizing constant and then this new normalizing constant that we've gone here. Plugging that in, we get these normalizing constants, and then all of the kind of vector counts for how many I think documents are labeled class 0 and class 1. So so this is going to be, let me just, I'm sorry, this is not documents. Basically, you plug this into the probabilities of the word vectors. Okay, so once you have that result, you plug that in to say like, okay, now that we have this concept of like, this document could be labeled 0 or the document could be labeled 1. Okay, we say, all right, what is the probability of this vector of word counts if it were document 0? And also, what's the probability of this word vector if it were labeled document 1, okay? But it's for the entire corpus here. So across all of the different kind of words, we say, okay, what is the probability of the corpus if it was labeled 0 versus probability of the kind of corpus if it was labeled 1, okay? And the authors kind of joke and they say, you know, I thought the point was to make it simplify, and this looks way more complicated, but it does reduce the kind of work when it comes to the Gibbs sampler. Okay. All right. So as we go forward, building the Gibbs sampler, it says the definition of the Gibbs sampler specifies that in each iteration, we're going to assign a new value to some variable that we want to draw by sampling from the conditional distribution, right? So we're saying if we want to draw from I, we take kind of all of our most recent values from 1 through I minus 1. That's going to be take the values at iteration t plus 1. And then for the values that we haven't sampled yet, that is zi plus 1 through zr, we're going to just use kind of the values that we've already established as well. So in our case, we are going to say, okay, let's draw a label, okay, for you know, document 1 or whatever, okay? Label for document 1, we're going to take a look at all of the labels from documents 2 through n, all of the other labels, the entire corpus, all of this stuff, all of the kind of established word probability vector at the latest iteration, word probability vector for class 1 at the latest iteration, all of the other kind of hyperparameters. Once we've reassigned label 1, or not reassigned, but drawn a new label for potential label for document 1. Okay, so document 1 could be either class 0 or class 1. Once we draw that, then we're going to incorporate this latest value of L1 to help us figure out what L2 is. L2 is going to use the latest value for L1. That's the only one that's been updated, and then we use kind of all of the older values for everything else. And we kind of keep going until we get through the, you know, kind of last value of here. Once we have all of the latest values for all of the document labels, then we'll go ahead and draw a new sample for what the theta vector is. Okay, so again, the theta vector is this, like, what is the probability of each word? Probability apple should show up is 25%. Probability cat shows up is 20% or something like that. Okay, so first we have to kind of resample all of the document labels, and we're going to kind of, basically, it's, again, this is document clustering, so we don't really have labels. So it's kind of like, we first start off with just, you have a whole bunch of documents, and you're like, okay, I don't know how this is going to work. So you just kind of randomly sort them into two piles. And we're going to say, this is class 0 and this is class 1, right? And then we say, okay, if all of these documents are class 0, how many times did apple appear? And how many times did cat appear? And how many times did dog appear for class 0? Okay, and then we, and based on that, we draw a new vector. And we say, okay, based on these counts, we're going to say, okay, I think apple should appear 25%, cat should appear 20% of the time, dog should appear this percentage of the time, okay? And then we do that with all of the documents labeled class 1 as well. But then, now that we have these kind of new vectors, and so we have theta 0 and theta 1, and so theta 0 says apple should appear 25%, and on theta 1 it says apple should appear 10% of the time, okay? And then we have, you know, probabilities for cat and dog and things like that for each of these two things. Then we go through and we say, okay, now that I have these word probability vectors, I'm going to go through all of these documents again, right? And I say, okay, what is the, in this document, apple appeared a whole bunch of times. So based on that, I'm going to, we'll do a random draw, but it'll have a higher probability of ending up in class 0, which had a higher probability for apple, okay? And then here's another document where apple appeared very few times, okay? And again, we still do a random draw, so it could end up in class 0 or class 1 by random chance, but the probability it's going to end up in class 1, where Apple has a lower probability, is going to be higher. And so we kind of, we go through and we redistribute all of the labels based on kind of the latest word counts. And we go through and then we resort all of our documents into 2 piles again. And then once we do that, we say, okay, now we go through all of the word counts. Now that I've resorted these into class 0 and these into class 1, I go through and say, how many times did Apple appear? And now Apple appeared like 800 times over here. And that's going to change my word probability vector for apples, cat, dogs, whatever we're looking at. Okay, how many times did apple, cat, and dog appear in this pile of class 1? And it's going to be different. And now that I get new kind of probability vectors for these words, I go through and I sort all of the documents again. And we kind of do this iterative we kind of take this iterative approach where we resample each of these document labels. And again, it's random sampling. So even though you might have like an 80% probability of class 0 versus 20% probability of class 1, because it's random, sometimes it will like randomly sample into the other class, okay? Or the less probable class. But anyway, you do all of these kind of document labels. Once you have all of these document labels, then you recalculate what your theta probability vectors are. Is that okay? I'm hoping to like help us interpret, because sometimes you read these papers and they just have all of this math and stuff, and it's like it's easy to just get lost in the symbols here. Okay, so let's see. Intuitively, at the start of iteration T, we have a collection of all of our current information, and this information includes the word count for each document, the number of documents labeled 0, number of documents labeled 1, word counts for all the documents labeled 0, word counts for all the documents labeled 1, current label for each document, the current values for our theta probability vectors, theta 0 and theta 1, etc. And we want to sample new label information for document J. So when we do that, we temporarily remove all information about this particular document from the collection of information. Okay, that is true. Then we look at the conditional probability that the document is 0, labeled 0 given all the remaining information, and the conditional probability that the document is labeled 1 for kind of that same information. And then so we draw a new sample by choosing randomly according to the relative weight on those 2 conditional probabilities, and then we sample new values according to the same principle. Okay, so how do we do the actual sampling? Okay, well, so basically this just says you're gonna, when you say, excuse me, when you say I want to draw, is this class 0 or class 1, technically you have to kind of remove the word counts from that one document. So, you say like, okay, this one document has a whole bunch of like, apple this many times, cat this many times, and dog this many times. We're going to remove those from the kind of current word counts of all of those labeled class 0 and all of those labeled class 1 have these probabilities here. Okay, I think that's enough to kind of get through. And yeah, once we have all of the labels, we can sample through theta and do all of this. Okay, so I've written this up. I've encoded this. It's under this document that says Gibbs Clustering Manual, and we'll walk through this. We'll walk through the code here, and I hope it all works. There's always a fear that the code you write just doesn't work when it's time to execute live, but I think I'm hoping it will. Okay. So I'm going to load up these 2 kind of text processing packages. One is TM, I think the text mining package, and then you have something called Snowball. and that does stuff. And to kind of simplify our document clustering, I'm going to have sets of documents. These are kids' books, and one is Green Eggs and Ham, and the other is Go Dog Go. So if you're not familiar, Green Eggs and Ham was written by Dr. Seuss, and I think it was a challenge from one of the kind of the publishers that said, see if you could, I bet you can't write a complete and compelling book with just 50 words or something like that. And Dr. Seuss took up the challenge and said, I'm going to write this book and I'm going to have just 50 unique words. And so it's about this character called I Am Sam, and he comes around and he tries to get the other character to try out green eggs and ham. And there's this back and forth of like, would you try green eggs and ham, in a box with a fox, or in a house or something with a mouse, so on and so forth. And they kind of go back and forth. So so I broke up the entire text of the document into, I think, 10 chunks here. And so like this first one, basically if you see like Sam or things like that, it's going to be likely to be about green eggs and ham. And so here's kind of like counts as one document, and it says, I do not like them in a box, I do not like them with a fox, I do not like them in a house, I do not like them with a mouse, I do not like them here or there, stuff like that. Okay, so that's going to be Green Eggs and Ham. And then there's another children's book called Go Dog Go, and it's just I don't know. Let me see if I can find Go Dog Go. Oh, there's a TV series. Look at that. Okay, this is basically, these are pictures from Go Dog Go, and they go, do we have the book? Go Dog Go book. Let's see if we have a preview. Oh, there's no preview of the pages. Okay, but anyway, it just shows like dogs driving cars and stuff like that. Okay. And then there, another book, Are You My Mother or whatever. Okay, but so if you try to read Go Dog Go, it'll be like dog, big dog, little dog, big dogs and little dogs, black and white dogs, and then there's this part that goes, hello, do you like my hat? I do not, goodbye. And then it keeps all of these things, right? It's just a picture, a red dog on a blue tree. And then there's another picture, a blue dog on a red tree, a green dog on a yellow tree, right? So there's like, these aren't real sentences. I mean, some of them are, and then they just have kind of pictures that go on. The yellow dog is down, the blue dog is in, the red dog is out. One dog up on a house, just stuff like that. Okay, so this is the advanced literature that we're going to try and cluster. So we will go ahead and read these in, okay? And I'm gonna just kind of put them all together into just this kind of, now I have a vector, 19 entries. Each entry is just one, is a character string with a bunch of text, okay? And right now our IDs, we're gonna have document IDs, documents labeled 1 through 19, and we have two classes, class 0 and class 1. So we'll say class 0 will be Green Eggs and Ham, class 1 will be Go Dog Go. And the way we have our text corpus set up is the first 10 are from Green Eggs and Ham, and the last 9 are from Go Dog Go. But, we don't know this just yet, okay? We'll put them all together into a data frame, and this is what my data frame looks like. well, it's hard to kind of, hard to see. So we're going to use these functions from the text mining package, okay? And this will take our data frame. So if you look at the structure of our data frame, it's just two variables, document ID and text. One column of just document labels 1 through 19. The other is just each one has these text here. And we're going to just turn it into a corpus, okay? Now the corpus itself, it's just a data structure used by the text mining package. Okay, it just says this is a simple corpus, right? And there are a whole bunch of kind of little functions that we can do. So one thing is there is the map function, text mining map function, and you can do things like make everything lowercase, remove punctuation, remove words, and then a big one is remove numbers, and a big one is we're going to remove English stop words. So things like the, to, a, is, things that don't generally add information, we're going to remove all of these stop words. I think not might even be, here, let's see if we can figure out what stop words in English are. Okay, so these are all of the English stop words that we're going to just kind of, it's going to go through and it's going to remove all of these things because these are just very common words that don't add a whole lot of information to clustering things. So, you know, I, my, myself, we, our, ours, him. These are all kind of very common, and we can't imagine English speaking without using any of these words. But as far as like clustering a document and classifying them, that's going to look like this. So right now, our document corpus, let's just do so right now, the document that started off as, you know, I am Sam, I am Sam, I am Sam, Sam I am, that Sam I am, that Sam I am, I do not like that Sam I am, has become Sam, 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 like Sam, okay? Because we got rid of, like, I do not like, or I do not like that Sam I am. Pretty much the only things that survived removing the stop words is like and Sam, okay? So that's one thing. And then we can do a stem document, okay? So let me just see if, let's look at like document 15. Okay, so right now, after removing the stop words, we have things like, hello, hello, do you like my hat? Just becomes like hat. I do not like your hat becomes like hat. Goodbye, goodbye. And then they talk about dogs, cars, going away fast, and things like that. Dog, I think it's like dogs and cars going away fast. Look at those dogs. Go, dog, go, or something like that, okay? We can stem the document, and what stem document does is it takes the words, and I think words like going just gets stemmed down to go. So we just drop all kinds of suffixes in this. So if I do stem the document, and we say, let's inspect document 15. So now going away just becomes go away, all right? Goodbye gets stemmed down to goodbye. I guess you can have like goodbying or something. I'm not sure, all right? So that's what stem document will do. We'll also strip white space. And then so this is, you know, like box, like fox, like a house. And so house, houses, those all get stemmed down to just H-O-U-S, but this is like house, houses, housing, housed, things like that. So that's what STEM document will do. So we will take this. This will be like how we've processed the words. So bag of words, we've taken our document, we've kind of shaken all of the words down, we've done all of this processing to kind of remove any kind of punctuation, remove the stop words, stem them down, and then we're going to create the document term matrix, okay? So the document term matrix is just going to be something that looks like this, and it's going to say, all right, document 1, these are, anywhere appears once, box appears 0 times, car appears 0 times, egg appears 3 times, green appears 3 times, ham appears 3 times, like appears 9 times, Sam appears 8 times, so on and so forth. So this will be the document counts, okay? Document 2 has these counts and things like that, and we can kind of see if any of this verifies. Let me zoom in. So I think, so this is document 1, and we can kind of see, does Sam indeed appear 8 times? I am Sam, I am Sam, Sam I am, that Sam I am, that Sam I am, I do not like that Sam I am, that's 6, blah, 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 Sam I am, I do not like them, Sam I am, yeah, okay, so Sam does appear 8 times. And then like, I do not like that Sam I am, do you like green eggs and ham? I do not like them, Sam I am, I do not like green eggs and ham. Would you like them here or there? I would not like them here or there. I would not like them anywhere. I do not like green eggs and ham. I do not like them, Sam I am. So indeed, like appears 9 times. Okay, and so this is just kind of going through our thing here, and let me see. If I do inspect our document term matrix, we have 59 words, 59 terms appearing in our document term matrix. And this is after we've thrown away a bunch of stop words, right? So again, that first document, if I do doc corpus 1, let me do inspect here. So again, this first sentence about, I am Sam, I am Sam, Sam I am, has boiled down to Sam, 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 like Sam. And then, and we go through, and then document term matrix, inspect our document term matrix. We'll just look at the first row here. This is the total word counts for that, okay? So I can take our document term matrix, make it a matrix, and so we have now 59 words here. So 59 columns and 19 rows here. So this is kind of what our term matrix looks like, and we can see, as the story progresses, it introduces more and more words, and so on and so forth. And we can kind of already see a little bit of the structure in here, like documents 11 through 16 here. This only shows the first 16 rows of the document term matrix. We have 19 rows because we have a total of 19 words, but there's no mention of mouse or box in Go Dog Go and so on and so forth. And then as far as Go Dog Go, looking at the word dog here, this column of dog, dog doesn't appear anywhere at all in green eggs and ham, okay? But in Go Dog Go, it's a very important word, okay, as one might expect. Okay, all of these other words, hello, little, 1, red, 3, white, and stuff, those don't appear in Go Dog Go. But Go Dog Go does take words like house and car. Those appear tree appears, will, I don't know, there are words, in common between the two things, okay? But our problem is, how do we cluster them? And again, we have no idea how these things should go in the beginning. We just kind of randomly sort them. They come in completely unlabeled, and we're going to ask the computer, our algorithm, to sort these things. I have completely ignored UQuiz answers, huh? Let me see. All right, I guess I'll give you all three of them right now. Your three ViewQuiz answers are A, C, and E. A, C, E, ACE. Okay, three ViewQuiz answers. So this is how we'll do it, okay? I gotta kind of go through this quickly. So one, we'll just count how many words are in the vocabulary. We have 59 words. How many documents total? We have 19 of them, okay? Our hyperparameters, we're gonna use uninformative hyperparameters. So for beta, we'll use a uniform. We'll just do 1 and 1, saying it could be any value between 0 and 1. And similar for the Dirichlet, our hyperparameters, instead of 555, we'll just have like 111, okay? But I've got 59 of these, right? Because I've got 59 words in my vocabulary right now. Okay, we're gonna just initially using setseed1, I'm gonna pick a random value for pi. The random value for pi is 0.73. That's just a random selection. Using that, I'm gonna just pick a random labels for our 19 documents. And so right now, my random labels, these are labeled 1, 0, a bunch of these are labeled document 1 or class 1, and some of them are labeled document class 0. So these are just random initial values. Using Dirichlet, theta 0, okay, theta 0 is a vector of length 59 because I got 59 words. All right, here, let me just round this off to like 2 decimal places. Okay, so because I've got 59 words, a lot of these words are have very low probabilities, but it's enough to kind of establish something. So I've got a theta 0, I've got a theta 1. Okay, so let me just generate these things. And then we'll go through and we will count all of the word counts in all of the documents labeled 0 and all of the documents labeled 1. So we're going to go kind of do our word counts. And then so looking at across all of the documents, so C0W is going to be like currently, based on all of the documents that are labeled 0, how many times does anywhere appear? How many times does egg appear, okay? And all of the documents labeled 1, how many times does anywhere appear? How many times does egg appear? How many times does green appear? These are my corpus counts. Based on my kind of current, these are, again, just initial random sampling values, okay? Because my clustering is because my documents are so simple, it ends up finding the proper clusters after just a few iterations, maybe around 15 here, okay? But let's just kind of look through what happens at each iteration. And this is the Gibbs sampler, okay? We're gonna kind of just take how many documents are currently labeled 1, how many documents are currently labeled 0, right? It's just we take the sum of how many things are labeled 1, and minus that is going to be how many are labeled 0. And then we're going to go through for each, we're going to get new labels here, okay? So for each of our different documents, I'm going to just kind of take out the word counts for this current document from C0W. So C0W is, what are the word counts if I remove, one particular label of documents, okay? And so, if that document is labeled 0, we'll subtract the word counts from C0W, and if it's not labeled 0, then we'll subtract it from C1. And then I go through, and this will just be kind of what are the what's kind of the new probability. This new probability for to assign a label to document J, right, is going to be based on kind of the old counts of how many are labeled 0, plus kind of our prior count. Okay, so again, this is count of successes and failures. These are just ones because we're using an uninformative prior, but you could generalize it to some other value here. And then we have total number of documents plus our prior values minus 1. And then down here is we have to take the product of all of our word counts. So this is theta 0, our vector, raised to the word counts. So we have the vector of each probability, and this is going to kind of give us, okay, what is the probability of getting a label 0 or a label 1 based on these word counts? So if the probability of dog for 0 is really low, okay, then when we look at the word counts in that particular document, so if I do word counts for document 1, okay, where dog doesn't appear anytime in word 0, and we say, okay, the probability of dog is low, then that's not going to be hindered, okay? Whereas if I go to, say, document 11, which has dog appear a bunch of times, and we say, what's the probability of getting that word dog, and it's really low, then that's going to reduce the probability of that thing. So we establish that, and then we're going to figure out, okay, what is the probability that we drew a 1 there, okay? And so once we use that, we're going to just randomly sample a draw. So it might end up being like 99% probability, but we don't want to say it's definitely going to be label 1. We randomly draw that. And then once we draw that label, then we go back and we add those counts back into the word counts, okay? And we kind of go through and we cycle through all of the documents this way. So we go through each document and we say, okay, based on the kind of the word counts, latest word counts, let's figure out the probabilities and establish that, okay? And then once we have the word counts, then we draw new theta vectors from the Dirichlet distribution. And that's that. So again, we just randomly sort them into 2 piles, not really looking. And then once we do that, we say, okay, this is basically the probability of dog for this pile, and this is the probability of dog for this pile. And then we say, based on that, let's resort our documents. And then we get like kind of new updated counts for dog and all of the other words as well. So we'll go ahead and we'll do, we'll run 15 iterations here, okay? And we can see, like for our first few, so in the beginning, we didn't know which ones were labeled class 1 and 0. Here is the labels across all 19 documents, okay? And after one iteration, at the next iteration, we got new updated kind of counts for each of these word vectors. And so at the second iteration, we have a lot fewer words or documents being labeled class 1. And you can see the document labels changing. Okay, document 3 kind of stayed labeled 1 the whole time. Document 14 stayed labeled 1 for a long time. So this is actually all kind of, I would say the clustering got correct at least, by the 8th iteration, really. So you can see how the labels have kind of changed. And so by the 8th iteration, it's clustering correctly. It has clustered all the first 10 documents into one cluster and the remaining 9 documents into the other cluster. And document 14, which is our 4th one, and go.go is the one that was kind of the slowest to cluster correctly. Let's see. Basically, this one has the vocabulary that is most similar to 1, 2, 3, 4. Okay. Oh yeah, so this one is the one that is least similar to the rest of go.go and most similar to green eggs and ham. It says the sun is up, the sun is yellow, yellow sun's over the house, it's hot out here in the sun, not hot in here in the house or whatever. Okay, so basically dog doesn't appear as much and house appears a little bit more often, where house is a word that is used in green eggs and ham quite a bit, where the word dog wasn't used at all in green eggs and ham. And because dog appears kind of the least number of times in this document, or very few times, the word dog does appear. Dogs at work, work dogs, dogs at play. It kind of got clustered last with everything else here. Okay, but anyway, I thought this was kind of a neat little thing. It can be generalized, and I generalized it using, I'm going to click Don't Save here, using, what did I use over here? I used JAGs in a similar fashion, and here I kind of mixed in a third cluster of documents, and this is from the children's book, Are You My Mother?, about a little bird looking for his mom. And so here I loaded in three sets of documents. So green eggs and ham, go.go, Are You My Mother? And we went through and did all of the processing here. But here I said, let's look for 3 clusters. And this time I just said, you know what, let's create a model using with the JAGs and OpenBugs thing. And we just said, hey, you know what, the document label will come from a categorical distribution, not binomial anymore, but it could be one of 3 categories. And then the word counts come from a multinomial distribution. And then the theta vectors come from a Dirichlet distribution. And if I run this, and I let the model run here, I think it classifies correctly. Last time I ran it, it classified correctly. So looking at our labels, so what we see is that these first 10 documents all got labeled to be class 2. The next 9 documents all got labeled to be class 1. And then the last 10 documents all got labeled to be class 3. Okay, so it is successful in kind of clustering these documents properly, even though when they come in completely unlabeled, as far as like these ones belong to this cluster, that cluster, that cluster. They come in unlabeled, but kind of using this process of, all right, let's just start with random sortings and then do word counts. And based on the word counts, we will establish like, a little bit kind of like this k-means clustering. Just we start off with random assignments, and then we just say, all right, this is kind of like where these are, again, not centered, but we just say like this, not the centroid, but we just say these are the word counts for this thing. So these words are more likely and these words are less likely. For this cluster over here, these ones are more likely and these ones are less likely. And using that, we kind of exacerbate any kind of extremes, and we say, all right, based on that, now this document is more likely to end up over here and this document's more likely to end up over here. And we kind of play off of that, and we keep cycling through kind of in this Gibbs sampling process, just updating at each iteration, and then things end up getting clustered accordingly as well. All right, so we'll wrap up here, and then so I guess on Wednesday we'll talk about what the final exam will look like, and we'll see you then.